So Dave asked me to talk a little bit about what's the value proposition of nuclear in this sort of new energy context with attention to climate change. So I'll talk a little bit about that. First part of my talk will be essentially the good news, why we like nuclear. Some of it will overlap with what you just heard from Karush. And then in the second half of the talk, I'll focus a little bit more on the challenges. No shortage of challenges with nuclear, as you may imagine. So the value proposition of nuclear in a low carbon world, again, Karush has alluded to this. Here you see the data. Life cycle greenhouse gas emissions for nuclear are actually pretty low. There have been many such studies that look at every step sort of in the broader fuel cycle, mining, construction, transportation, operation, decommissioning, waste disposal, everything included. When you look at metrics such as the amount of CO2 emitted per unit electricity generated, so grams of CO2 equivalent per kilowatt hour, nuclear ends up being pretty low. And not surprisingly, at the other end of the spectrum, you have fossil fuels, which emit as the energy is generated. Karush also told you about the land, and we all use maybe somewhat different metrics, but nuclear is very compact overall, and that comes from the things that he's just explained. It's a very high energy intensity source, but also the fact that it operates essentially all the time. You heard these words, capacity factor, okay? So it's pretty reliable. It can operate for several years without refueling, essentially all the time at full capacity. Okay, so if you now focus only on low carbon energy sources, and so nuclear, solar, wind, hydro, geothermal, etc., and you look at how they sort of stack up against each other in different parts of the world, you can see that roughly worldwide, the nuclear takes about 30% of our low carbon electricity source or electricity production. Wind and solar maybe 20-25%, and then close to 50% worldwide is hydro. So we'll still rely very much on that ancient technology. Nobody mentions hydro, but hydro is still sort of the workhorse of the power industry worldwide, with the exception, of course, of coal and others. In the United States, roughly 50% of our low carbon electricity comes from nuclear, and then you can see hydro and solar at the other level. In China, they're big on hydro. EU as a energy picture, when it comes to low carbon energy sources, which looks a little bit like the US, with nuclear taking on a majority of the share, and then hydro a little bit less, and solar somewhere in between. And then the last set of bars that you see there is for the Republic of Korea, South Korea. I had that because I give presentations such as this one's all over the place, and they asked me to show how much they're relying on nuclear. You can see that in Korea, again, restricting our attention to low carbon energy sources, they get close to, I think, 85% for nuclear and very little from others. So it's a potpourri, sort of a checkerboard situation. Some countries rely more on nuclear, some less. And so if you look at the big trends, we see clearly this technology growing in places like China, India, Russia, the Middle East, and we expect Eastern Europe. And if you look at Western Europe, Japan and the US has been more or less stagnant over the past 20 years. And I'll get into why that's been the case for a while. So this slide is meant to sort of make the point that nuclear is already a big part of our low carbon energy infrastructure. So the question now is, what do we do going forward? Do we keep nuclear we have? Do we want to grow it? Do we want to, reduce it, etc.? So I would argue that if you have a technology that works well and already provides, 20+% of the total global energy, low carbon electricity, you probably want to keep these plants running. And I'll make the point here that it's actually a very attractive economic proposition to keep them running. This is the example of Spain. It's a study that we did 6 years ago for the Spanish government. Spain has currently 7 reactors, so 7 gigawatts of nuclear capacity, and they're all expected to expire, their operating license to expire within the next 5 to 10 years. And so the big question for Spain is, do I make the investment and keep operating these nuclear power plants, or do I allow for that expiration to sort of take place and then shut them down? So there is an investment. There is it's not free if you want to extend the license of these reactors. And so we evaluated that and found out that it takes roughly 35 euros per megawatt hour once you make that investment to extend the life of the nuclear power plants by 20 years. But what are you comparing it with? Well, in this particular study, we compare it to all solar replacement, all wind replacement, and then two scenarios with 25 and 75% solar and wind respectively. So those are the columns on the right. And of course, when you do that with solar and wind, you gotta add storage in the form of lithium-ion batteries, because you need to keep, to basically manage the intermittency. So, as I said, about roughly 35 euros per megawatt hour if you keep the nuclear plants, and the best you can do with the other scenarios is roughly twice as expensive. Okay, so this is not to say it's nuclear versus renewables. It really isn't. We need to add renewables to nuclear, and we have to add more nuclear to the grid. We need everything, okay, because the magnitude of the challenge that we're facing here in terms of decarbonizing, the power sector, and more broadly the energy system, is such that you can't afford to throw away one energy source or the other one. So we need everything. But the point here that I want to make is, if a country already has nuclear power plants, it's actually a very, very good investment to extend their lifetime. And this is what we're seeing, what we've been seeing for the past 20 years, and we continue to see in the United States, for example, and now also in Europe. Now, a very interesting question, of course, is you don't have nuclear power plants. Do you want them going forward or not? Is it a good investment or not? Well, let me just give you the punchline here, and then I'll explain the plot. So, what our modeling and modeling done at this point by many other organizations around the world show is that excluding nuclear energy can actually drive up the average cost of electricity in low carbon scenarios. Okay, so let me explain this a little bit better. The plot that you see there on the left is average generation cost. So this is dollars per megawatt hour, this is US dollar per megawatt hour. And it's in the context of a very populous region of China, near Tianjin, Beijing, Tangshan. They have fairly expensive natural gas, and they have unfavorable renewables because it's a relatively high latitude. It's fairly, Beijing is fairly northern location. And the different bars that you see there refer to different scenarios. Blue is a scenario that excludes nuclear. So the model basically says you're not allowed to put nuclear in the energy mix, in the generation mix. Orange says include nuclear at we call it nominal cost, what has been the historical cost for new nuclear in China. And then the gray scenario is nuclear with the postulated arbitrary 20% cost reduction, okay? The model really takes in the energy need, the energy demand in this particular area, 8,760 entries, one for each hour. So it's the hourly energy need in this market, okay? And then it takes into account also the hourly availability of solar and wind in that region based on historical data. So at that particular date or that particular month, how much solar and wind can you expect? And then it takes in, as part of the input, also the cost of the individual energy generators, electricity generators. So nuclear, solar, wind, natural gas, carbon capture and sequestration. It crunches all these numbers, and then it spits out a generation mix, okay, that basically minimizes the cost of electricity in that particular area. And that's what is plotted there, average generation cost dollars per megawatt hour. Now you can do this, you can repeat this model for different carbon constraints. So you can say, okay, at the moment I got 500 grams of CO2 per kilowatt hour, but if we're serious about decarbonizing, I need to go to less than 50. I need to reduce the emissions by roughly 90%. Let me finish it. And so basically what you're seeing here is that scenario where nuclear is excluded, the average cost of electricity in that market goes up exponentially as you're trying to reduce the emissions. Whereas if you keep nuclear, if you have some nuclear in the mix, it stays more or less constant. Now you may be wondering, I'm getting to the question, you may be wondering, why is that? Because nuclear has sort of a reputation of being expensive. It is expensive. And in fact, the first challenge that we're going to talk about is reducing cost of nuclear. But while being expensive, it is one, low carbon. Number two, it's basically always on. So if you're trying to decarbonize the electricity system without something that looks like nuclear, that is essentially reliable and low carbon, what are you left with? Solar, wind, and batteries. Now, because of the intermittency issue, if you're only left with those three technologies, you have to overbuild the system. You have to overbuild the capacity of solar, wind, and batteries to make sure that a megawatt hour that is generated, I don't know, in February here on February 12th here in Australia is available to be used when the demand actually occurs, which may be a month later or whatever. And so it's the aggregate cost of all that infrastructure that raises the cost, the average cost of electricity, unless you have something that looks like nuclear in the mix. Yes, sir. Yeah, these are US dollars, and the analysis here was done in 2018, so you gotta escalate things appropriately or scaling them depending on which country you're in. The figure on the right simply says what I just said. This is the scenario without nuclear, and if you don't have nuclear, the total capacity, total installed capacity of those technologies increases dramatically as you drive down the carbon constraint, because you need basically that overcapacity to handle the intermittency. So that's the end of the good news for nuclear. So that the big value proposition is it's certainly clean, doesn't take a lot of land, and when introduced in a properly balanced generation mix, it actually helps to reduce, to keep costs reasonably speaking. All right, so what are the challenges? Well, the main challenge I'm going to discuss today is two of them. One is real, the other one is sort of perceived. The real one is that the high initial construction cost of nuclear. Okay, so particularly large nuclear power plants are expensive to build. They require a big financial commitment up front, and depending on who builds them and where they build them, it could take for as little as, say, 4 or 5 years, and as long as over a decade. Okay, so that is a very, very important financial commitment. So the current business model for nuclear, which really entails lengthy testing and licensing. If you have a new idea for a reactor, even if it's a pressurized water reactor that Karush was telling you about, if the design is substantially different in some details, some important details than what was done in the past, you're looking at a fairly lengthy period of testing and then review by the Nuclear Regulatory Commission or by the nuclear regulator, and then finally the licensing. And then these are typically built in the field. So these become large construction projects, okay? Akin to a dam or akin to a big highway system or whatever you can think of. And then when it's all said and done, you got this awesome machine, very large plant, 1,000 plus megawatts. But what are you really selling? You're selling a commodity. Okay, now things maybe are starting to change a little bit on the grid. Not all electrons are created equal, but for the longest time, once the electrons are on the grid, nobody really cares where they're coming from. That's a commodity market. Okay, so now think about this in terms of investment proposition. You go to a community of investors and tell them, give me a few $1 billion, because that's what we're talking about, per reactor, and 10, 15 years later, I'm gonna sell commodity electrons on the grid. Not a very attractive proposition. Not a very attractive proposition. Okay, so if this is a big national infrastructure project with that kind of commitment, long-term commitment, it makes sense. That's how it tends to be in Asian countries, in China, in Russia, in India, etc. These are now becoming infrastructure projects that the government is very committed to, and so that provides that stability, that horizon of 10, 15 years, which makes these things attractive. But if you are sort of in a true sort of laissez-faire free market situation where the market is free to pick whatever energy generators they think is the cheapest, then this becomes a little bit tough, okay? Which is why here it says economically problematic in the US and Europe, which tend to be that way, although things are in flux because government policies are in flux about energy. So a little bit of a 5-minute tutorial on cost in nuclear. So it's not a perfect metric, but the levelized cost of electricity is a good enough, certainly for this discussion, metric to look at, to compare cost of different energy generators or energy generating technologies. So if you look at nuclear, roughly 70% of the levelized cost of electricity, and levelized cost of electricity is roughly defined as all the costs associated with building the plant, operating the plant, decommissioning the plant, fuel, everything included, that's the numerator, and divided by the total energy or total electricity generated by that plant over the lifetime of the plant. Okay, it's properly discounted in terms of time value of money and things like that. But the essential idea of levelized cost of electricity is that ratio. Okay, all the cost at the numerator, all the energy generated at the denominator. So that's LCOE. And if you look at that for nuclear, 70% of it is in building the plant, including financing. So that's really the heavy lift. Then maybe 20-22% or so is to operate and maintain the plant, including physical security, which at least in the United States has taken a growing fraction of cost, a lot of armed guards. And then finally, paying for the fuel is typically less than 10%. Okay, so nuclear power plants have been, I think, correctly referred to as expensive machines burning cheap fuel. That's very true. If you look at this breakdown of the cost, it's mostly building the plant, then operating it is not that expensive. Very different cost structures, for example, with respect to natural gas, which mostly you're paying for the gas itself. The fuel is expensive, building the plant not that expensive. And then for solar and wind, it's all about building the plant and then operating it and maintaining it, because of course there is no fuel cost associated with solar and wind. Yes? No, this is the levelized cost at what we call the bus bar. So it's, you have a power plant, and if you just measure the cost of that electricity coming out of the power plant, that's what is shown here. When you factor in things like transmission, distribution, and all the auxiliary infrastructures, then I'm back to the slides that I showed a couple of slides ago, where you were looking really at what we call system costs. And I think that's the appropriate way to look at it. Okay, that's why I said LCOE is not perfect. Okay, but for the purpose of my discussion here, it's important that you guys understand where is the cost associated with nuclear, and it is very much in building the plant. Good question. Now, if you look at the breakdown of that building the plant, okay, building the plant is a generic. What does it really mean? All right, so these are three different designs. The acronyms here don't mean anything to you. AP1000 is an American design. APR 1400 is Korean design. EPR is a European design, okay? They're actually all large pressurized water reactors, the same type of reactors that Karush told you about. And in a study that I ran back in 2018 on the future of nuclear, we looked at what is the cost breakdown for building these three different designs, okay? And we did this through interviews and analyzing the data that are publicly available for these different designs. And you see the results here. Essentially, all three designs, whether they are Europe, US, or Asia, from the point of view of the breakdown of the capital cost, they look very much the same with small differences. So the first disappointing result or finding from this study is that the direct cost of the equipment in what we call the nuclear island and the turbine island, in other words, the reactor pressure vessel, the pipes, the wires, instrumentation and control, etc., is only 20 to 25% of the total cost. Those are the dark blue and red slices of that pie. Okay, why do I say this is disappointing? Well, because just like Karush, I'm also a nuclear engineer, and I've spent all my life, dreaming up different reactor designs, and with the hope that, you would reduce the cost, that there is some kind of a silver bullet, a magic design out there that will reduce the cost. Well, no. I mean, of course, good design is extremely important, and it might help with some of the cost drivers, but it's not mostly about the direct cost of the components. Okay, so what is it about? You see that the largest slice of the chart here is that light blue. It's oddly called yard cooling and installation. This is the terminology used by Black and Veatch for their study on the AP1000. But what that really means is all the work associated with preparing the site, excavation, foundations, all the civil works, the containment structure, reinforced concrete, which costs a lot of money, the labor associated with it, the oversight, the site oversight for the construction, the engineering, and all of that. So that's roughly 45 to 50%. And then you look at the two other slices you have there. One is green, is the engineering procurement. That's all the engineering that goes on prior to the, or even during building the plant. And then lastly, owner's cost. This is things like the cost of the land itself, insurance, and things of that type. What this chart actually excludes is a big indirect cost, which is financing. So what is this not showing is actually the interest during construction. And if you added that one, it would make the non-direct cost component of this breakdown even bigger. Okay, so keep that in mind as we move forward with the conversation. Okay, so You might have heard that some of the recent projects in the West, and that I mean US and Western Europe, have gone disastrously bad in terms of cost and schedule control, doing things on time and on budget. Whereas in Asia, things have gone much better. And that's actually true. So what is shown here is the overnight construction cost. These are now dollars per kilowatt of installed capacity. And you see essentially two groups there. One on the left is the Asian projects in South Korea, in the Emirates, and in China. They routinely bring new nuclear power plants online at an overnight construction cost, let's say between $2,500, $3,000, and $5,000. Okay, and if you do that, that ends up being pretty cheap nuclear. That's actually pretty attractive. And then on the right, you have the European and US projects. AP1000 in the US, EPR in the UK, France, and Finland. And you can look at the scale there is roughly twice as high. So you may be wondering, why are the Asians so good? Why are folks in Asia so good at building these plants, and why are we so bad? And you may be tempted to think that it has something to do with the technology. Maybe they're building better reactors. They found some kind of design that is better than ours. And the answer is absolutely not. In fact, we're all building essentially the same machines. They're all large pressurized water reactors, with a few exceptions, okay, with high degree of complexities. And so, again, as part of the study that I keep mentioning, we looked at what are the reasons for the big changes or the big differences between Asia and the West, and we sort of boil it down to the bullets that you see on this slide here. So I'm going to just comment on a couple of this so that we can move on with the conversation. The first is almost comical. In Asia, the companies that build these plants never break ground and start building the plant until they finish designing it. Okay, and the type of design that I'm talking about here is the detailed design. You guys know that there are different, different stages of design. There is pre-conceptual, conceptual, preliminary, and then detail. I'm talking about the final detailed design that goes down to blueprints that you can pass on to fabricators and contractors and say, build this thing for me. Okay. That level of design, which is very needed for construction. In the case of US and Europe, for the project that we've seen, they had sort of a completion of that type of design of less than 50% when they started. Whereas in Asia, like I said, they're much more disciplined. They don't start building it until they've actually finished design. You may wonder, why is there such an obvious mistake was made in the US and Europe? Primarily commercial pressures, and in the case of the US, some sort of schedule for getting government aid in the form of loan guarantees that basically push the companies to rush into construction when they weren't really ready. The second bullet is something fairly inevitable. In Asia, Korea, China, and Russia, basically they have been building continuously nuclear power plants for the past 30 years, so the supply chain is rather mature. In the US and Europe, for 20 years or so, there was no new build, so the supply chain evaporated. And then when we restarted building it, well, it had to be the supply chain itself had to be rebuilt, and that was certainly an issue. And then the last one I'm going to comment is the third bullet. In Asia, these projects tend to be a lot more vertically integrated. Often the company that designs the plant is the same company that builds it, it's the same company that eventually owns it and operates it. And so by being more vertically integrated, you have better chance of including fabricators and constructors into your design team. And so to ensure that what you're designing is actually constructible. I have several examples that I could give you about the AP1000. That's the American design built in the US, where the technology development company, which is Westinghouse, very capable company, they ended up doing the design of some parts or some modules, some components, and then pass it, literally, sort of toss it over the fence to their supply chain, and then supply chain was not able to build it for them, and that's because there wasn't that sort of integration between the two teams earlier on in the process. So this is all to say that it has very little to do with the technologies. It has almost everything to do with good project management practices and really getting sort of a plan in place to make things successful. In the interest of time, I'm going to skip the aggravating factors. I'll just mention this one because I'm sure it's on everybody's mind. You may also be tempted to think that in China, nuclear power plants cost less because their labor rates are lower. That obviously does make a little bit of a difference. You can quantify that, and I'm not going to tell you how we did it, but we did it, I think, properly in less than $1,000 per kilowatt. So it's not insignificant, but if you think about the other plot that I just showed you, what was the difference in terms of dollars per kilowatt between the, say, Chinese projects and the US project? 4,000 or 5,000. Okay, so this business of labor rates at most accounts for 20-25% of the difference between US and China, but it doesn't explain why the difference is so big. What I've just talked about for the past 5 minutes, that's the real explanation. Okay. All right, so having said that, going forward, how do you reduce the cost? Well, the first and most important thing is that you start implementing those good project management practices, okay? So, but then there are also some, perhaps a little bit more technical things that you can do. The first is gonna be very underwhelming. I don't care what you're building. You're building a large reactor, you're building a small modular reactor, you're building a pressurized water reactor or a high temperature gas reactor. If you build the same thing, exactly the same thing, over and over again, and you're doing it at one site, so you're not building one unit here, another unit there, another unit at the third, but you build 3 or 4 at the same site, the cost of the subsequent units is lower than the cost of the first unit. Okay, that's because basically you have the workforce, they learn, the management learns, and they do, the second time they do the job, they do it better than the first time. We have overwhelming evidence in this, even in dysfunctional projects where you look at the overall cost is very high. If you have 2 or 3 units at the same site, you can clearly see unit 2 is costing less than unit 1, unit 3 is costing less than unit 2. So this idea of a fleet, this idea of repetition is very, very powerful. Incidentally, the second picture that there is the Palo Verde, again, the Palo Verde plant in Arizona. 3 identical plants, and unit 3 was a lot cheaper than the other one. Now, I already mentioned a lot of the cost is in concrete structures, in sort of what we call the civil works. So ways to reduce the cost of reinforced concrete are good ways to also reduce the overall cost of the plant. Okay, so in a traditional reinforced concrete structure, you need to basically create a rebar cage. That's the steel bars that go inside the reinforced concrete. Then you put the formwork, then you pour the concrete, then you let it set, and then you strip off the formwork. That is very labor intensive and it takes a lot of time, but there are ways to sort of either eliminate or reduce the number of steps associated with erecting reinforced concrete structures. One that seems to be quite popular now is to use steel plate composites. So what these are essentially steel boxes that are now made in factories. Factories tend to be high productivity environments as opposed to construction sites, which tend to be low productivity, fairly inefficient environments. So you're shifting a significant scope of the project from a construction site to factories. You don't need to do that for the whole reactor. That's on a grand scale, but you can do it for individual components, and that usually tends to reduce cost and maybe manage the schedule a little bit better. So the steel plate composites, these boxes, then they can be basically welded together at the site. You pour the concrete and off you go. So fewer steps, less need for labor at the site. Seismic isolation is another interesting one that we expect. I don't think that anybody has truly quantified yet how the cost reduction is going to be, but we expect seismic isolation to actually reduce cost. This may seem counterintuitive because when you seismically isolate a structure, you're actually adding some components to it, the seismic isolators themselves. But what that allows you to do is that what you build on top of the seismic isolators now becomes basically independent of which site you are on, because you are, well, as the word says, isolating it from the local earthquakes, if you will. So this is a tool that basically allows for one, standardization of the nuclear island, the reactor itself, because it's no longer site dependent. And number 2, it allows for a lightening of the superstructures, because the support for components, et cetera, don't have to be as strong as they would if they have to take the full acceleration of the full motion of the ground, basically. So that's one other approach. All these approaches are reactor independent technology, right? So as I said, I don't care what you're building, they all work. Maybe becoming a little bit more creative, you could integrate reactors into floating platforms or barges. Why would that be on a slide about cost? Because shipyards, just like factories, tend to be high efficiency, high productivity environments, once again, as opposed to construction sites, which are not, okay? So, and this also allows for a little bit more nimble business model, if you will. You build the plant entirely in a shipyard, and then you float it, you literally float it to a coastal site, and it's gonna be there for, I don't know, 10, 20 years, whatever is the duration of the project, and then you can move it to another site. So it becomes a little bit more flexible asset. And also in terms of the back end of the project, you can bring it back to a shipyard where it's gonna be decommissioned. So the site that actually used the energy would be returned to greenfield, if you will, almost overnight, okay? So it simplifies some things. And finally, the most popular approach of them all, you've heard small modular reactors. You hear this word modular all the time in the nuclear community, and it could mean different things to different people, but the only modularity that, in my opinion, makes sense is in the context of construction, okay? And so what we mean by modular construction here is the following. Traditionally, nuclear power plants have been built by bringing raw materials and individual components to a construction site and then start assembling it and building it at the construction site. The idea of modular construction is that you prefabricate, pre-assemble large modules, entire systems, or potentially even the entire plant, but let's say entire systems, in high productivity environments like shipyards and factories. And then you ship those big modules to the site and you connect them. So all of this is meant, again, to shift scope of work from a construction site to more efficient environments. These approaches have been tried by other industries, and they have resulted in cost reductions in the range between 10 and 50%. For example, large module pre-assembling is common practice in chemical plants, and very close to the topic here, even in nuclear submarines. So the Virginia class submarines that the Royal Australian Navy will get as part of AUKUS are now built modularly, okay? They've been built more and more modularly over the past 10 years, and they've seen a nice construction cost reduction in schedule by 20-25%. So it's relatively proven approach. It's mostly a matter of translating this to the civilian sector. Okay, so that was the first challenge. The second challenge is a little bit more perceived, but it's sort of the curse of our existence. It's high-level waste. Why do I say the curse of our existence? Because even with people that are, become convinced that nuclear is great, there is always this objection: what about the waste? What are you going to do with the waste? Okay, so you'll see that I'm fairly positive on on how we handle it, but I'm happy to have a conversation. So first of all, what we call waste is really the spent fuel. Okay, so again, you've seen from Koroush, what comes out of what is used as a fuel assembly in the reactor core is basically that array, or sort of that assembly of fuel rods. Within each fuel rods, you got those fuel pellets made of uranium dioxide. That's where fission takes place. And when you got fission, you also have the fission fragments, which are highly radioactive and stay radioactive for a long time. So the spent fuel that comes out of the reactor still looks the same, by the way. So just the first myth to dispel here is that nuclear waste is some kind of greenish goo that sort of oozes out of barrels. It could be, it couldn't be further from the truth. That is the high-level waste. That's the waste. That's the spent fuel. So it still looks the same, but it's radioactive and it's pretty hot. So what do you need to do? Well, first order of business, at least in the US, we put it into spent fuel storage pools. You can see one such pool there. These are usually co-located they're always co-located with the reactor itself, so they're adjacent to the reactor itself. And there it sits between 3 and 5 years, during which radioactivity naturally decays off, and also what we call the decay is reduced substantially, to the point where you can transfer these fuel assemblies from a wet storage situation to what we call dry casks. And so you can see a bunch of these dry casks here. These are essentially cylindrical canisters made of steel with a little bit of concrete surrounding it. And the concrete is mostly there to provide shielding against the residual radiation that is still emitted by those fuel assemblies. Okay, so outside these casks, basically you can go there, hug them, spend an afternoon, and you get very little radiation. I'll show you on the next slide. But, and this has already been remarked, the first thing that we need to understand is how much of this waste is produced. Not much. And why is that? Because if you understand that the waste is the spent fuel, and you understand how energy intense uranium, the spent fuel, is, then it's a logical step to understand why we're not producing a lot of waste, okay? Because it doesn't take a lot of material, a lot of uranium to produce a lot of energy to begin with, and therefore you don't have a lot of that spent fuel, that spent uranium, with the fission products at the end to produce that energy. So the volumes are not high. To give you an example here, if I had a 1,000 megawatt reactor, which would be enough to power, at least in the United States, a city of 750,000 people, or let's say 1 million people, just to round it up. Over 60 years, so imagine the city of Boston, where we live here at MIT, over 60 years would be powered only by nuclear. You would have 80 such dry casks. That would be it. That would be the total amount of spent fuel or waste that you've generated, okay? So these dry casks are very, very safe. It's a mature technology. We've now used it in the US for, I think, close to 40 years. The image on the left is a class that I used to take to a local dry cask storage area at the Pilgrim Nuclear Power Plant, which is now being decommissioned, and it was the most boring field trip ever. And that was the point of the trip. It says, that's it, okay? So in those dry casks that you see behind us there, that's the dreaded nuclear waste, okay? So not a very exciting material. There are dry cask storages at other 60 sites throughout the US, because essentially they're co-located with each nuclear power plant that we have. And even after decommissioning, those dry casks can basically stay at the site. What you see there is the site of the main Yankee, up still in New England in the Northeast. The nuclear power plant is gone, has been fully decommissioned, and there are two things left. There is a switcher there, which they kept as part of the grid net, and then you have that, what I call the parking lot, and you can see a bunch of those dry casks there. And the reason why they're still there is because the ultimate repository where that material eventually will have to go in the United States, we don't have it yet, okay? And that's really where the conversation becomes very negative about waste, because so far I've shown you, it looks very harmless, very sort of plain vanilla. It's a bunch of casks like that. You can go there and nothing really happens. But eventually that material's gotta go somewhere, and the consensus is that it goes underground, like other toxic waste. Eventually you wanna put it underground. Why is underground the preferred disposal method? Any guesses? Because it reduces the mobility, okay? So if you put things underground, they don't tend to sort of be volatile and being spread into the biosphere, etc. Not that this material has a particular propensity to do that, because it's solid, you've seen it, it's inside those fuel assemblies. But the idea here is that it has to basically be immobilized for thousands of years, so that until its radioactivity goes away. And so you put it underground. And in the US, we have a site which is called Yucca Mountain in Nevada, which was identified 30 years ago, where the federal government said, okay, that's where we're gonna put our dry casks. And then the political process was so mismanaged that basically now we're at a point where the state of Nevada says, no way, we don't want it in our state. And I don't think Yucca Mountain is gonna happen. So we're back to square one in the US. We need to decide where all those dry casks here from these sites are gonna go eventually. But mercifully, the world is not like the US, and so you have other countries where this process has been managed a lot better. They tend to be countries in which the government enjoys a higher level of trust by the citizenry. In the US, as you can imagine, is an all-time low, okay? But there are places like in the Nordic countries, Scandinavia, Sweden, Finland, where there is a little bit more of a trust for government. And so they've managed the process much better, and Finland is gonna be the first country that actually opens a final permanent repository underground. I think you have a talk as part of this program by Atte Arjana. He's a member of parliament in Finland, so he will tell you a lot more about that. But so this can be done. The point here is that yes, it's an issue. Certainly, it's a perception issue for the public. It's a social acceptance. But one, is not particularly difficult from a technical point of view, and two, if the political process is well managed, there are examples that show that it can be done. Okay, so how it's going to play out in Australia, I don't know. But you guys will have to work it out whether you decide to go with civilian nuclear or not, because AUKUS will produce, minuscule amounts of this waste, and you got to do something with it. Okay, so eventually you'll have to. All right. So how much time do I have? I'm looking at Dave. How am I doing time-wise? He's not here. Anybody? I should look at you. I'm sorry. You're at the MC. How much time do I have? Just so that I can. Only a couple of minutes. Okay. All right. So I need to accelerate. So I have here a section on technologies and markets. Let me actually skip this because some of this is redundant with what you heard. And I want to really go to this one here. So if Australia was to, decide to go with nuclear for civilian beyond AUKUS, what's in it for it? What's the value proposition of nuclear specifically for Australia? So this plot is the South Australian equivalent of what I show you at the beginning of my talk for China. Okay, it's the same model. It shows the same thing. It's the average cost of generation dollars per megawatt hour. The x-axis is the same thing. It's the carbon limit. It's the carbon restrictions, grams of CO2 per kilowatt hour. And here you see 4 scenarios. One is get to keep this is all for South Australia, so we use data from South Australia. Brownfield with wind with no nuclear. So whatever wind you have, you get to use it, and you don't allow nuclear to participate. Then you have gray is greenfield wind. So in other words, you have to build all your new wind capacity and then no nuclear. And then the orange and yellow are now allowing nuclear to be part of the mix. Okay, and you can see sort of a similar trend of what I show you for China. If you don't have something like nuclear in the mix, which is low carbon and it also is sort of always on, then the average cost of electricity in a place like South Australia, as you try to decarbonize, escalates. And this was done in 2017, if I remember correctly. And my understanding is that South Australia has gone down this path of everything's got to be renewables. And my understanding further is that indeed the average cost of electricity in that state has gone up and up and up. Okay, so this was a model that we did before. It seems that reality is pretty similar. Now, we've been talking about nuclear for the grid, but nuclear is a source of heat to begin with, and electricity doesn't have to be used on the grid. It could be used more locally. So one use that I think could make sense for Australia, which I know very well because I've been visiting and touring left and right as a tourist, literally, is that it's very arid. And there are areas where you might find it attractive to maybe convert some of those arid areas to agriculture and make them a little bit more productive. So that can be done through water desalination. And just to give you an idea of the scale, a 300 megawatt nuclear reactor, for example, BWRX 300, one of these SMRs, would be able to produce about 2 million cubic meter per day, or 730 million cubic meter per year of desalinated water, and that's enough, according to our calculation, to render suitable for agriculture a semi-arid area of 5,000 square kilometers. Okay, so we did this study again for South Australia. It was a part of the Eyre Peninsula. We looked at areas that are not completely desertic, but they're dry enough that currently you could not farm, and what would it take to farm it? Okay, and one such reactor basically could make an area of 5,000 square kilometers fertile. We went further and postulated a couple of crops that you could make in that area that would be compatible with the soil and the climate and all of that. And you'll find this sort of mundane, but potatoes are actually pretty lucrative if you sell them in Japan and China. Prices are pretty high. So we did the whole sort of simple techno-economic analysis. This would pay for itself royally. So imagine that. So on our side, South Australia becomes potato farm for China and Japan, making a ton of money. And all you need is one reactor, 300 megawatt, which is really pretty small. The technology exists, is used very, very extensively in many countries. The biggest user of freshwater desalination coupled with agriculture in a desert situation is Israel. And all of this is done at a very, very low carbon footprint because the energy input required to desalinate water comes from the nuclear plant. And so just to be quantitative, 50 grams of CO2 per cubic meter. With nuclear, without a world's average now, desalination would be 2,000 grams of CO2 per cubic meter. You have a bunch of mining sites around. That map there shows all the major mines that you have in Australia. Not all are equally big. The one that is shown here is, I think, Olympic Dam. That's the largest. Olympic Dam alone would require, for the expansion that they planned there, 640 megawatts of new electricity, 640 megawatts. Olympic Dam is at the end of again, South Australia, you see I got a thing for South Australia. It's at the end of a transmission line. And so Either you build it very, very far, but then you got to sort of transmit it thousands of kilometers away, which costs money, or you could build it. In situ, and their nuclear power plants would really make a ton of sense. You already know that Australia supplies a lot of the nuclear fuel to the world. This actually shows the reserves. I think you said just that it's about 1/3 of the total. We could sort of add up the bars. I think it's probably about right. It's not the cheapest in Australia. You see here the different colors show the range, and so at the moment, part of why Australia does not dominate the uranium market. It's a big player, but it doesn't dominate it. Is the cheapest uranium is not actually in Australia. It's in Canada and Kazakhstan. So you look at the production is higher there. Just to put some more numbers there, in 2022 in Australia, produced about 10% of the world's uranium, and it was $1 billion Australian export value added to the economy, and about 3,000 jobs. Okay, which again for a small country like Australia is pretty significant. Now this is maybe a little bit more ambitious, but you have a lot of land, a lot of capabilities here, as was explained by Jazz already, and so actually securing spent fuel for the world may be a major economic opportunity for Australia. It's ideal arid climate. You have a lot of remote locations. You're a signee of the NPT. You have also a good international reputation, unlike the US, not of being bullies, being a little bit more easy to deal with. And so what's the market size? So, there is not yet here a legal mechanism by which, for example, the US could send its spent fuel for final disposal here to Australia. But you can look at what the utilities are currently paying every year to manage the dry casks, those boring cylinders there that I show you, $1 million US worth every year. And so, at a minimum, if I was Australian, I had something like this and I wanted to become sort of the hub for spent fuel, I would charge at a minimum $1 billion per year to do it there. I'm truly coming to the end here. So this has already been mentioned. If we're looking at what's the value proposition for Australia. Australia already is and will be a major nuclear player because of AUKUS. Okay, and so the question is, does it make sense to leverage the capabilities that will be built for AUKUS also in the civilian sector? I think there is a lot to be said about that. My favorite is probably to, they provide job opportunities or prospective career opportunities for people that will come out of the AUKUS program when they're done with, being sailors or whatever they do as part of AUKUS, and then having a civilian nuclear industry that has jobs for them that are well paid and leverage their expertise. Okay, so we've seen this in the US for many years. All right, this is a long series of bullets here just to sort of tell you that the interest in nuclear over the past 2 years has grown dramatically. I've been in this community, in this business for over 25 years, and I've seen a lot of ups and downs in terms of support and then, sort of rejection of nuclear, but I've never seen so much support as there is now. It's not a foregone conclusion that nuclear will grow. Many things can still go wrong, primarily the fact that the industry, at least in our countries, has not been very good at building plants, as I mentioned earlier, so they can still screw things up. But it's looking good for all the reasons shown here. So the last one here is, so having said all of that, I hope at a minimum that you can have a serious conversation about nuclear energy here in Australia again. I know there is a ban that goes back 20 years. To me, banning a technology a priori is pretty dumb. You don't want to ban them. You want to keep it open and have the conversation. You can still make the decision not to build, but have a ban is a pretty bad idea. So hopefully Australia will reconsider, and we'll see. So with that, I'm stopping and happy to take any questions you might have.